Flash memory was invented in the early 1980s by Fujio Masaoka while working at Toshiba. Since then, there's been an explosion in these storage devices: micro SD, standard SDs, flash drives, M.2 and SSDs. These all work on similar technologies but are physically different and different in their use. Everything we know is made up from atoms, from a feather to the sun. At these subatomic levels we have two basic objects: the electron and the nucleus. These particles have some special and unique properties and relationship. The electron, which has a negative charge, orbits the nucleus just like the moon orbits the Earth. This is a very loose comparison. The number of electrons vary through different substances. For instance, here we have just one electron that orbits the nucleus. The nucleus causes the electron to behave in this manner. More about the nucleus can be learnt through Google search. Our main interest here is just the electrons. This atom is called the hydrogen atom and is the simplest form of an atom. The next atom up has two electrons and is called the helium atom, the beryllium atom, the carbon atom and the oxygen atom. The denser the substance, the more electrons it has. This is the periodic table that outlines the number of electrons with each element. The ones we have pointed out are hydrogen. We can see here it is number 1 in the periodic table. Helium, beryllium, carbon and oxygen. But we can see here others that we have come across, such as copper, as used in electrical cables, or gold, that is used in motherboards and most electrical contacts. So the higher the number in the periodic table means more electrons and better conductivity. Of course, there are many millions of atoms that create even the smallest particle. Let's have a look at the movement of electrons. In an ideal world, these atoms are balanced, so the overall electrical charge is neutral. If an extra electron is added to the atom, in our example we have made it blue for clarity, the atom then becomes more negative and unstable, rejecting the electron to return it back to neutral. Now let's take a series of atoms and our rogue electron. It joins the first atom in our example, and this atom becomes more negative and unstable, so it rejects it. This electron then joins the next atom, and it too becomes unstable, and so on until all the atoms that inherit an electron rejects it and becomes stable once more. We have only shown just the one electron, but in practice it's many millions. It's the flow of electrons that causes electricity. We are showing the world of electrons as orderly and organised, but that is far from being the truth. Most electrons are in a state of chaos, and stray electrons can cause an unbalance. These stray electrons can happen naturally, or we can influence them. But what happens if two electrons on the same flight paths head towards each other? Remember, they are both negatively charged. This would avoid the collision because two like poles will never meet, so normal electrons do not collide. Once again, we can influence this if need be. Okay, let's take the next example. This time we have two bunches of electrons, and when one meets the other, the smaller bunch makes way for the larger ones. We can see here 12 electrons. It's almost 2.5 times stronger than our second bunch of 5 electrons. So the 12 electrons will force its way past our smaller bunch. Again, there are other factors that we could take in consideration. One major factor would be the speed of the electrons, but let's not get tied up with that. We just need the very basics. The flow of electrons can pass through some objects easily. These are called conductors. Some examples are gold, silver, copper, iron, aluminium and steel. In other objects, this flow is slowed down or blocked, and these are called insulators, such as rubber, wood, fabric, air, glass and plastic. A typical conductor is copper wire, and a typical insulator is the rubber or plastic sleeving that surrounds it, that is found in domestic mains cables. It's the flow of electrons which is our interest, and how we can influence the direction and flow of them. The concept of flash and SSD memory is to trap the electrons. It's not really a new idea, as we've been doing it for many years with batteries, storing electrons in them and releasing them to power devices. And even if the batteries are not used, they will in time lose their charge as they are not completely insulated. So to create flash memory, what specifications do we need? A container. Be able to fill it with a charge or electrons, seal it so there is no leakage even when power is removed, test it if it's empty or full, and be able to empty the container. So we can see how our flash memory is built. Let's find a container. Be able to fill it with electrons, seal it tight so there is no leakage even when the power is removed, be able to test it if it's empty or if it's full of electrons, and of course be able to empty it. Now we shall create the MOSFET, or metal oxide semiconductor field effect transistor. This field effect transistor was first patented over 100 years ago, 1925, but it wasn't until 1934 that it was finally invented. It's the principle that allows flash memory to work. This is a typical MOSFET, and it has 3 pins: source, drain and gate. The one shown here is about 30mm high. Naturally, modern MOSFETs fitted in flash and SSD drives are microscopic, are in their thousands and millions. So here is our container. It is called a floating gate. We shall not concern ourselves on the materials we shall be using, just the theory on how the MOSFETs work. This is where we shall fill it with a charge or electrons. We have to seal this so there is no leakage from the floating gate even when power is removed. So this is achieved with an insulator above and below the floating gate and around it. This is a very special insulator, unlike wood or plastic, which brings us to an interesting problem. We must have a way to know if the floating gate is full or empty. We just can't open it, since this would allow the electrons to escape. Also, we can't test it with a meter because it is sealed with an insulator, but we know the electrons repel each other, which will be useful. First, we need to get the electrons into the floating gate. We do this using a silicon substrate just below the lower insulator. 2 terminals are placed either side of the substrate, called source and drain. For our electrons to cross from source to drain, it must have a minimum voltage, or if you prefer, a minimum voltage to push the electrons across this gap. This is called a threshold voltage. Also, if the electrons make a successful route from source to drain, then the digital output will change. We shall reset the digital output. This time a much higher voltage is applied to the source, and because of this more of the electrons are forced from source to drain, which causes some of the electrons to pass through the lower insulator and be trapped in the floating gate. The power is again removed, and now the floating gate is different as it now holds a negative charge. That causes a negative field between the source and drain. Remember what we said about when 2 electrons meet? Let's test it and see what the outcome will be. Again, we shall be using the threshold voltage. Remember, this is the minimum voltage we can use to make the electrons cross over from the source to the drain. Because the floating gate now holds a negative charge, the electrons cannot cross over from the source to the drain. This means the digital output is now 0. We need just one more component to complete our MOSFET, and that is the control gate. When a high negative voltage is applied to the control gate, the electrons in the floating gate are repelled back into the silicon substrate. Now when we rerun the test using the threshold voltage, there is once again a clear path from the source to the drain, which results into digital 1. Here we have two states. MOSFET 1 currently has a digital output of 1. We can see that when the threshold voltage is set and the electron path is clear from source to drain. To change MOSFET 1 to digital output of 0, a high voltage is applied to the source, causing the floating gate to accumulate a negative charge. This also exists between the source and drain. When the threshold voltage is applied to the source, the electrons fail to cross over to the drain, resulting in the digital output to 0. MOSFET 2 is currently set to digital output 0, since the electrons cannot flow between the source and drain. To flush the floating gate, we apply a negative voltage to the gate, repelling the electrons back into the silicon substrate, removing the negative charge. This means when the threshold voltage is applied to the source, the electrons can make a successful connection between the source and the drain, resulting in a digital output of 1. One really important point here is that when a large voltage is applied to the control gate to repel the electrons back through the lower insulator, it is weakened. This also happens when a large voltage is applied to the source. So we can see the end result is that the lower insulator will ultimately fail, which means the gate will not be able to hold its charge and corrupting the data. Again, we are only looking at one single bit. A common use for micro SD and SD cards are mobile phones, tablets, cameras and drones, mainly because of their size. These are more prone to data corruption and should never be relied on as a backup. A flash drive is primarily used to transfer data from one device to another. Once again, there is little or no protection against data loss and should only be used as a temporary storage. The SSD uses a command called trim that optimizes the SSD performance, reduces wear and extends the drive's lifespan, and is considerably faster than conventional hard drives. Currently, the ultimate storage is the M.2 SSD, as it is normally installed within the computer or laptop. Access and retrieval is almost instant, and once again has the trim command.